We have a talk from Atac now. Yeah, please. 1 hour.
Okay. Yeah, I'll try to finish in 1 hour. So before I start, I'd like to sort of thank my co-workers and really want to highlight two names that is very sort of dear to this community, Richard Schmidt and Eugene Demner. And it's really through our discussions that many of the ideas that we utilize in the experiments were developed. So the angle in my talk would be a bit different, that it would really be about not so much about the fundamental properties of polaron physics, but really more to use mobile exciton impurities as a spectroscopic tool. And so basically what I'm going to try to show you is that exciton-electron interactions can be used to do optical spectroscopy of interesting, strongly correlated electronic states. So the idea would be that one starts out with an interesting electronic state, and then you introduce a low density of impurities via an optical excitation. Now, the issue, though, is that these interactions, at least in 2D materials, are generically weak, and which is a limitation for spectroscopy, as you will see, but it's also a limitation for our longer-term goal of generating or studying degenerate Bose-Fermi mixtures of excitons and electrons. So what I'm trying to say here is that the ability to enhance and control the exciton-electron interaction strength using external electric or magnetic fields would be very highly desirable. So, and again, it's this community knows very well that this is what the atomic physicists do very well, using Feshbach resonances, and I do not have to say much about it, but the bottom line is that one needs a closed channel which supports a molecule, and then such in order to control the interaction of particles in the so-called open channel or the scattering state. So what we wanted to address here is that can we really develop these ideas and find analogs in 2D materials? So the starting point is that since I'm interested in exciton-electron interactions, if I consider a monolayer, the situation looks rather bleak, because basically we have, this would be the effective potential that describes exciton-electron scattering. And I will say a few more words, but exciton is a strongly bound pair of an electron and hole. And so the interaction is attractive with 1 over r to the 4, and it supports a bound state. And this bound state has a very strong binding energy of about 25 milli-electron volts, which basically excludes the possibility that one can use spin orbit coupling and tuning the other state with magnetic field. This would require probably about 100 Tesla type magnetic fields, which we do not have access to. So basically what I will try to show you is I should also say that this bound state between the exciton and electron is called a trion, and I will also say a few things about this, but this is the analog of the H- ion. And there is absolutely a single bound state, at least at zero field in these, at least as far as I know in the systems, although Francesca might say more about that. So, so basically what I'm going to focus on is that I'm going to try to show you that if we do not deal with the monolayer, but with the bilayer system, then we can actually introduce a second channel and study Feshbach physics or realize Feshbach physics. Okay, so what I will do, though, I will start out with describing to you elementary optical excitations in transition metal dichalcogenides, and how the impurity description or a description of excitons as impurities, or how and when it becomes relevant in understanding this spectrum. Then I will tell you about using such a mobile excitonic impurity as a sensor of charge order in a Wigner crystal of electrons. And then in the latter part, I will tell you about the observation of the 2D Feshbach resonance. So let me tell you a few things about the material system. So I will be focusing on transition metal dichalcogenides, monolayers. So these are layered semiconductors, much like graphene with strong covalent bonds in plane and weak van der Waals coupling between the layers, which allows us to exfoliate layers, monolayers or bilayers, and then stack them at will to create a interesting, or what we find to be interesting, heterostructures. So again, these transition metal dichalcogenides have a wealth of different properties, but we'll be focusing on the semiconducting ones, and in particular, molybdenum diselenide is the material of choice in my group. And the main reason for that is that it has the nicest, cleanest optical transitions. Okay, so, and I should also say that in case you're not familiar with the system, what I refer to as a monolayer is actually a tri-layer system where molybdenum, triangular lattice of molybdenum atoms is sandwiched in between selenide layers of selenide atoms. So if you look at it from a distance, we have a honeycomb lattice where the A sites, say, are molybdenum and B sites consist of a dimer of selenium atoms. Okay, so in that sense, it's a graphene model, but with the description would be a massive Dirac model because of the fact that A and B sites are very inequivalent in this system. Okay, so what I failed to say is that at the monolayer level, all of these semiconductors are actually direct bandgap. And therefore, they have nice optical properties. And what I would like to highlight again is that when you consider a direct bandgap material, in this case, I should have said K or K prime, but this depends on, of course, the material that is of interest. So basically, what we have is that because of the interactions in the system, the dominant features in the optical excitation are not free electron hole pair transitions. This is the case in traditional materials at room temperature that we use for lasers and whatnot. But at low temperatures in all materials and for TMDs at practically all accessible temperatures, the dominant excitations are excitons. So basically the bound state of the electron that we excite with the hole that it leaves behind. So these excitons are very tightly bound and consequently have a large oscillator strength, and they dominate the absorption spectrum. I should also say that in an ideal system, at least, that these excitons in this monolayer have a center of mass momentum, let's call it K parallel, and basically this is a good quantum number. And when they decay to generate a photon, the photon has to have the same in-plane momentum. Okay. Now, why I'm making this trivial statement? Yes. Is there a question or?
Yes. What's the size of the exciton compared to the monolayer thickness?
Yeah. Okay. Excellent. So I was going to say it here. That's why I didn't say. So the monolayer thickness is about 0.5 nanometers. The separation, the lattice constant is about 0.3, and the Bohr radius is 1.1 nanometers. So these are, let's say, vanilla excitons, but on the verge, right? So we describe them as vanilla, but the length scale difference between the Bohr radius and the lattice constant is not so large. And that's a point here that if you are interested, that for the very same reason that for at least for the 1s exciton, the lowest flying excitons, the Coulomb potential does not provide a good quantitative description of the electron hole attraction. So one really needs to use a Ryotova Keldysh potential to take into account that when the electron and hole are very close to each other, that they're subject to the electric field lines are subject to strong screening, which is no longer the case if the exciton size becomes larger. And I should say that these numbers are determined by diamagnetic shift experiments at magnetic fields up to 65 Tesla. and therefore HBN embedded material. So this is not just a suspended monolayer, but it has hexagonal boron nitride on the two sides, which has an index of 4. So if one did not have that, the binding energy, even though there is no accurate measurement of this, in my opinion, would be around 500 milli-electron volts, and the Bohr radius should go down to about 0.7. Okay, so the point that I wanted to make with this momentum conservation is that the excitons have their own dispersion, which can be approximated as a parabolic dispersion for low momenta. And what is important, though, is that only the excitons with the lowest momenta, with momenta on the order of the photon momentum, can decay radiatively. So the higher momentum excitons, which are normally generated in a relaxation process, are dark towards radiative decay. Okay, so if we do such an experiment, the photoluminescence experiments where we generate with the high energy photon, free electron hole pairs, these would relax and form high momentum excitons and then relax down to form an actual exciton on timescales of a few picoseconds and then decay as an exciton on some timescales of sub-picoseconds. But before they find the k equals 0 exciton state, right? So in these longer lived states, if there are free charges, or even if they are trapped but loosely trapped, then the exciton can actually bind to an existing charge, say an electron, and then form a trion, this bound state of 2 electrons and a hole. And this will then, even though it's a, let's say, even if the density is low, the oscillator strength of such trions are low, they can really show up prominently in the photoluminescence spectrum, as you see here, due to the fact that they provide the lowest energy states for optical excitation. Okay, so now that was my general introduction to this material system. So what I would like to describe to you is how we make measurements. So for the last 4 or 5 years, we no longer just take a monolayer and look at its optical properties, but rather embed this in a simple heterostructure, which is defined not only by the boron nitride layers, but also top and bottom gates. And these gates are typically graphene or a few layer graphene, and that we use to independently control the electric field, the vertical electric field, and the chemical potential in the layer. For a monolayer, the electric field is not so important, but this does become important for bilayer systems. Okay, so, and as I already mentioned, that if we do not have charges in the system, if the chemical potential is inside the gap, then the optical excitations are tightly bound excitons. And this is precisely what you see here. So this is essentially a plot, a color-coded plot of the reflection from the sample, which measures absorption or spectral function. And what you see is that for gate voltages, when there is charge neutrality, when there is practically no source drain current running through the system, then you see a dominant exciton feature that here color-coded but it does tell you or show you that the reflectance of this material can be on the order of unity. Actually, if you design your material properly, the resonant reflection could be as high as 30 times above what you would get without the exciton. So these couple extremely strongly, excitons couple extremely strongly to the incident light. Now, if you increase the gate voltage, you start injecting electrons into the system, and then you see that there's a source drain current running through the system. And when that happens, the exciton blue shifts and broadens, and then there is a new resonance emerging at a lower energy, which picks up an oscillator strength. And where this guy starts out is precisely the trion energy that we see in photoluminescence. So without charges or with unintentional doping in this regime, in this charge neutrality, we do not see any absorption features of trions. Okay, so I think for this community, I guess this really is no surprise that what we're dealing with are attractive polaron and repulsive polaron branches And that's what basically we introduced together with Eugene to understand the spectral features of the system. Yes.
In this spectrum, you seem to have the trion peaks rather deeply into the charge neutrality region. Why is that happening?
Yeah, so that's a good point. So so this actually varies from sample to sample, but the explanation is this, or tentative explanation, let me say, because we haven't done enough of the combined transport and optics experiments to make a definite claim. But for this particular sample, I expect the electrons here to be either localized in defects, and therefore they do not really contribute to current. So basically, I guess what I'm trying to say is that we inject carriers. It's just that these carriers are not mobile. And as you will see, I mean, I think this wasn't a particularly good sample, so I don't think there was a Wigner crystal of any size, measurable size in this system. But the other sort of possibility for seeing a difference between, let's say, the current and the optical response would be that if the electrons form a pin Wigner crystal, then again, this is what you would, this would be the response that you would like to see. Because basically, the optical dressing or dressing of optical excitations to zeroth order does not depend on the mobile nature of the electrons. And you'll see this in the Wigner crystal experiments. Okay. So that said, I mean, when we model, we assume the electrons to form a degenerate Fermi gas, and then we describe the interactions using a contact interaction. So there is essentially nothing new to this community, except to say that, of course, we determine the effective contact interaction strength through the binding energy of the trion. And what I would like to highlight here is that the trion we can always think about as a bound state with a certain wave function of an exciton and an electron. And the trion is actually, unlike atomic molecules, it is relatively tightly bound. So the size of the trion is on the order of 2 to 3 nanometers, which in turn means that if you look at it in this as the superposition of exciton-electron pairs, that the decay rate or the oscillator strength of the trion is going to be extremely small due to the fact that trion can only decay due to its low momentum or zero momentum exciton content, right? So the tighter it's bound, then the probability of finding an exciton with low momentum is going to be correspondingly low, and therefore the trion decay rate would be correspondingly longer. In return, though, of course, finite momentum trions can also decay because of the fact that there is the probability of finding the zero momentum excitons would not really appreciably change. Okay, so again, so most everything that I say in this talk would be can be understood using the Chevy ansatz. So in that sense, from let's say the Fermi-polaron perspective, I'm not saying so much new. Maybe I should highlight that something we did not know is that in the exciton community, Robert Souris actually proposed such an ansatz to describe excitons in the presence of electrons in 2,6 semiconductors, actually even before Frederick Chevy. But this somehow did not really resonate so well in the community, and I learned it after I learned it. I learned about Chevy ansatz, even though I work in this field. Okay, and
do you say that you actually in reality never go beyond the order of expansion showed in this formula? So you don't need extra terms, so it works so well for.
Yeah, yes, I think at least for experiments that we carry out with in the Fermi-polaron regime, that is when we consider dressing of excitons with electrons, we haven't really seen any reason to go beyond dressing with a single electron hole pair. I must say that we also have done experiments on Bose-polarons, which I'm not going to talk about. And there we also, these are relatively new, but there's also sort of no evidence for a state with wherein bosonic impurity binding two bosons. So in that sense, but these are more preliminary experiments. So, but in the fermionic case, yes, that seems to be the case. But you should also keep in mind that, I mean, my emphasis will not be so much on sort of corrections to the energy and how well we can describe, or whether there are sort of significant deviations from the predictions of the Chevy ansatz. So, as I said, the perspective is to use these impurities as sensors of the interesting physics. But you can turn it around and say that to zeroth order, whether the starting state is a Fermi sea or is something more interesting like a Mott-Wigner state or a sort of a state consisting of Wigner crystallites, doesn't really affect the energy of the polaron substantially. Okay, so I'll show you the data.
Thank you very much.
Yeah. So again, then this is another take. I guess I'm not saying so much that is new here. I guess what I want to point out is that the attractive polaron resonances in properly designed and clean samples can be extremely narrow. Actually, they can be narrower than the excitons, which is not a surprise, of course, because its spectral weight is determined by the quasi-particle weight. But in the solid state, this is kind of a nice, welcome sort of, maybe not a surprise, but a feature, let's say. And so again, two things I would like to emphasize, that basically looking at the strong electron density dependence of the repulsive-polaron, so one can see that one could use the repulsive-polaron resonance as a way of sensing what is happening to the electrons. And again, at this way, this is like a very mundane sensing, just the density. So it looks, the energy increases with the density, but I'll try to convince you that there is more in the details. And maybe another feature is that for the attractive polaron, so it's basically for the latter part of the talk, I would say that this is our way of sensing the presence of a molecule in the system. And the other point that I want to make here is that you see that it first redshifts and then starts blue shifting. And this is a characteristic feature because of the fact that you know, excitons and electrons in opposite valleys actually interact to form trions or attractive polarons. But at zero field, we fill both valleys with electrons. And when that happens, then the exciton energy is renormalized due to phase-space filling effects. And that's why there is eventually a turnaround and the blue shift. Another factor that actually bothered me a lot, and maybe also Mira as well, is so all of this theoretical model is based on this rigid impurity assumption, right? And then we also know, particularly from gallium arsenide, that whenever we have electrons, excitons are, the electron hole attraction is screened, and then the excitons ionize. So what we have shown by three different measurements is that up to 10 to the 12, the Bohr radius only decreases by about 20%. So the exciton binding, or the exciton, remains essentially unaffected in the presence of the electrons, justifying this picture of dynamical dressing a la Chevy. Okay, so now what can we learn about electrons or hole states using exciton polarons? So the trivial one is the density of the electrons can be measured. We can measure the degree of electron or hole spin or valley polarization, which is interesting in the context of because we have measured giant paramagnetism, and there are hopes or claims that we might be able to see even itinerant ferromagnetism in the system. which I believe is not settled yet. There have been beautiful experiments from the Cornell group of Jishan and Qinfei Mak showing that actually the excitons in one layer, Rydberg excitons in this case, can sense the compressibility of electrons or holes in a neighboring monolayer. And in our experiments, we actually dealt with the monolayer and used the excitons or these excitonic impurities to provide a direct evidence for charge order. So what is the picture then in using these cartoons? So if you have an undoped system, this is the excitonic dispersion. The devil is in the details. If you go outside the light cone, actually the excitonic dispersion splits. There's a transverse exciton mode and the longitudinal exciton mode. Longitudinal scales linearly and therefore is not terribly relevant for what I'm going to tell you. Now, if we introduce electrons into the system, and if these electrons are in a liquid state or a disordered state, then the main effect is this repulsive-polaron blue shift which changes with density. So basically, neglecting some changes of the effective mass, that the main effect is, which we can not really see because we only have access to the zero momentum excitons, at least in this regime, we only see this blue shift due to repulsive-polaron formation. But if the electrons actually were to form a Wigner crystal state or any periodic ordering of charge, say due to also the existence of an external potential, as is the case in moire systems, then the excitons will now see a periodic potential, and therefore their dispersion is now going to be defined in a reduced Brillouin zone, and the band folding or Bragg umklapp scattering would basically result in new resonances that are optically active, because these folded bands at k equals 0 of the reduced Brillouin zone would mix with the true k equals 0 excitons and will acquire a finite oscillator string. Okay, and that's what we want to use. That is basically the impurity in the presence of periodic charge distribution should see a periodic lattice structure. And if we can probe the excited states of excited bands in the structure, then we should be able to obtain a direct evidence for it. Now, the actual band structure is more complicated than the simple 1D description. So this is the actual band structure that we expect to get. So this we calculate using it's relatively simple treatment, very simple treatment by treating the electrons as providing a Hartree term for the excitons. And so the main point is that in this yellow shaded light cone, in addition to the k equals 0 modes, we have 2 out of these 6 modes becoming optically active. And these are the guys that we should look at. Now, if you look at them with the bare eye meaning just look at the reflectivity, this is again another sample, another plot as you go from neutrality to electron doping. Well, in this case, to first order, you don't really see much. Even though at these low densities that I'm quoting here, if you look at the RS parameter, it exceeds 30. Okay, and this is due to the fact that the dielectric screening is low and the effective mass of the electrons is high. It's actually higher than what the DFT predicts. It's on the order of 0.8 times the free electron mass. But if we now differentiate this data with respect to the voltage, then what we find is that there is actually a resonance that is on the blue side of the repulsive-polaron resonance, and its difference from the repulsive-polaron increases linearly with the electron density. And if you look at if we try to plot this resonance or the difference between the resonance energies as a function of the electron density, the proportionality constants actually give us the exciton mass, which is known from prior measurements. And this is basically is in very good agreement with the expected values. So basically, we can say that this linear dependence is a very strong indication that this new resonance is associated with the emergence of a periodic structure. But we can also look at the temperature dependence, because we do expect the Wigner crystal to melt around 10 Kelvin, according to Ilya's estimates. And indeed, so the results that I was showing you before, these are at 80 millikelvin. So here, actually, I should also mention that the EF over T is on the order of 100 or larger, even at these low densities. So, so this is at 4 Kelvin, the resonance becomes a bit weaker, and at 10 Kelvin, it's hardly visible. As we go above 11, it becomes completely indiscernible. This happens actually while the excitonic resonance hardly gets modified in terms of its energy and line shape. Okay, so that's basically sort of what I wanted to share with you in terms of usefulness or interest in using mobile impurities as a spectroscopic tool for what happens in the to the electrons. I hope I convince you that we can detect charge order. We also have some theoretical work unpublished yet, which shows that we should be able to also see spin order in these systems, which would then, of course, be very interesting if we can really study the transition from, let's say, a liquid state to a Wigner crystal state, and what happens to the spin order in those intermediate states. But maybe to make this the motivation for the next topic, so even at the lowest temperatures, you see that this resonance is very weak, and the reason for that is that the exciton-electron interactions are very weak, and you can say that is due to the fact that in the single channel model, the molecular state is far out, and the effective repulsive interactions between excitons and electrons is relatively weak. So we want to be able to change that, right? So the idea then is that we could go to a bilayer system, which is very interesting in its own right, way beyond being able to tune interaction strength. So the structure that I'm going to show you now has actually 2 layers of molybdenum diselenide with a very small twist angle in between. So I should also say that this wasn't intentional, but it's as particularly when you have a boron nitride in between the 2 layers, it is very difficult to set the angle with very high precision. But we know that this is very close to 0 because it's prepared using the so-called itinerant stack technique. So now, in this system, we have a new degree of freedom, which is whether the electron or hole is in the upper or the bottom layer. And the same applies for the exciton. But again, our emphasis is on using excitons as a probe, as a sensor. So what we also sort of happily notice in the system is that even though these are really the same monolayer, same like 20 micron size monolayer that was torn apart and then stacked, the exciton energy is differing depending on the position by as much as 7 milli-electron volts. And that we believe is due to the strain on the material, which modifies the exciton, and it can modify the exciton energy sizably. So in other parts of the sample, the energy difference goes to 0 or even crosses that the bottom layer becomes lower in energy. But this is our best spot, and every sample has a best spot where the lines are narrowest. So this is where we work with. So the point that I'm trying to make here is that we have basically a knob on the system, which is the exciton energy, which tells where the electrons or holes are. So here, for example, you see that for this particular backgate voltage, or for this particular change of top and backgate voltage, we see that we first inject electrons into the top layer that we see because of the repulsive-polaron formation there, whereas the bottom layer does not really show either a repulsive-polaron or an attractive-polaron. And only at a higher gate voltage, we start to dope the bottom layer as well. And then we can also go to different sort of electric fields where we actually either dope the bottom or the top layer, etc., etc. So now the electric field becomes essential because it basically determines, as we increase the chemical potential, where the charges will go first. And that, as I said, we can basically determine by looking at the optical response. Okay, so we basically therefore have a way in the quantum information language, a way to measure in the computational basis of the pseudo-spin. Okay, I don't want to exaggerate this connection, but basically the point that I'm trying to make is that we can determine the layer pseudo-spin of an electron or a collection of electrons in this way. And then if we also have interlayer tunneling, then this would be a way to manipulate this layer pseudo-spin. Okay, so now let me show you what happens to this material at large electric fields. Okay, so this is another take on the data that I was showing you. So what I'm doing now is I fix the electric field, and even though this says top gate voltage, what I'm really doing is I'm changing the chemical potential, right? So basically there is the neutral regime, and then I can either electron or hole dope the top layer, and the bottom layer exhibits a small redshift, but that's it. It doesn't exhibit the attractive polaron. So this is kind of repeating what I said before. Now, if you go to a regime where the electric field is close to zero, then, and if you focus on the attractive polaron side, the story is very different. And what we see is that in this case, that we have actually multiple attractive polaron resonances, not only those like this one for the top layer that basically only changes its strength as we change the electron density by transferring the charges from one layer to the other, but also the new lines that basically strongly depend on the applied electric field. Okay, and this is due to the fact that for the hole, which we do not see on the electron side, but what this is really showing, telling us is that at least some of the holes that we have in the system are subject to coherent tunnel coupling, which hybridizes the whole states in the two layers and results in this dispersing lines. This becomes a bit more clearer when we look at photoluminescence, where you see that there is this anti-crossing behavior for each layer for the whole state. So in photoluminescence, this is the final state. So the physics that I'm showing you here is very simple. It's a single particle effect. The whole states, the holes that we inject into the system can actually hybridize and occupy symmetric superposition states, and that results in new blue-shifted attractive polaron resonances because symmetric state formation lowers the energy of the holes and therefore increases the polaron energy. In emission, we also see a decay into the anti-symmetric superposition. That's why we also see the redshifted peaks. Okay, so now let's look at the picture on a larger scale for this filling factor of 3, meaning this means that we have 3 holes per moire side. So the regime I showed you before is this sort of low electric field regime. And what you see is that actually something interesting happens as we increase the electric field, deplete the holes from the top layer. Right, so the whole at this electric field, there are no holes in the top layer. That we can say because there is no attractive polaron resonance, and all the holes are transferred into the bottom layer. And yet we see that there is a sort of a signature of an anti-crossing between the top layer and let's call it a ghost attractive polaron resonance for the time being. Okay, so if you focus in here, and we change the density, we see that for nu equals 2 electrons per lattice site, we see that something is cooking, and it becomes clearer as we increase the density. And for nu equals 3, one can now really see this redshifting branch and the onset of this very asymmetric anti-crossing. So I claim that this is a direct signature of a Feshbach resonance, and the Feshbach resonance occurs for a scattering state that consists of a top layer exciton and a bottom layer hole. And as these guys, for these gate voltages, the energy of the scattering state can be tuned into resonance with a molecular state which consists of a trion in the top layer. So the picture is like this: this is our scattering state, exciton in top, hole in the bottom layer. When they overlap, and if we have tunnel coupling, we can do a virtual excitation of the trion in the top layer. And what the electric field does is that it allows us to tune the energy of this top layer trion into resonance with the scattering state. Okay, so again, in using the schemes that people use in atomic physics, our closed channel then is an exciton and a hole in the top layer, which supports this bound state, and open channel is when they are in different layers, and we bring this this bound state into resonance. Okay, so I claim that actually the way we see this bound state and the formation of a Feshbach molecule, remember that we have a truly 2D problem, so we always have a bound state in the system, and basically the energy of this line, which is the attractive polaron associated with the Feshbach molecule, is telling us basically roughly where the Feshbach molecule is. Okay, so this is a theoretical modeling which agrees reasonably well with our experiments. Basically, the main difference is that while it shows the asymmetry, the theory that the attractive polaron branch extends out further and the repulsive polaron disappears more quickly in the experiment, it does also disappear relatively quickly according to the theory. Okay, so now what I would like to do is, I mean, of course, what we want to do is that we want to use this enhancement of interactions to basically, first of all, for mediating interactions between holes in one layer using excitons in another layer, and this could be used to, for example, induce ferromagnetic interaction between holes, and in the long run, we hope to generate strongly correlated Bose-Fermi mixtures. But before I finish my talk, since I'm a bit early, I would like to also say that these ideas have, in my opinion, have a much more general applicability in the 2D material systems. And this is, so for that, I would like to show you sort of my interpretation of a recent proposal by Valentin Krepel and Liang Fu. So where they discuss superconductivity using purely repulsive interactions. So they consider a bilayer system. So the A lattice, denoted by the blue, is they assume to be a mode state in the bottom layer, and B lattice is largely unoccupied, and and one considers now injection of electrons into the top layer which are then nominally free particles that can hop between different p sites, right? So the Coulomb energy cost of having this excess electron in the top layer in the presence of the bottom layer electrons is already paid by the gate voltage. Now, there are sort of, in addition to these free electrons, which again, whose scattering will define our open channel, there are other excitations in the system. For example, an electron can pull up an electron from the A lattice and bring it into the B lattice. So this is what Leon refers to as a charge transfer exciton. And then he defines this, this object consisting of a hole left behind in A lattice and 2 electrons as a polaron. Okay, and then if you have 2 electrons in the B lattice nearby, and if they pull up a charge transfer exciton, then they can form this object called trimer. Basically, 3 electrons in B lattice surrounding a missing electron in the A lattice. Now, if you consider a polaron and electron in the A lattice in the top layer as a closed channel, this channel does have a bound state, which is the trimer state, right? Because the energy of a polaron plus electron can be lowered if they were to form this bound state. And basically, we can then understand and tune the energy of this trimer state by applying a gate voltage to bring it closer to the energy of the scattering state. And then the electrons can form Cooper pairs in the BEC regime, and we can understand these as the Feshbach molecule occurring due to the presence of virtual excitations into the trimer state. So, of course, the analysis doesn't require this picture, but I think it's kind of nice to make this connection and see how actually one can use these ideas in real electronic systems and even without optical excitations to understand regimes which are potentially of interest for superconductivity. Okay, with that, I will stop and thank you for your attention. So
right. I understand that you can use the transverse the perpendicular electric field to tune a hole and an exciton into a Feshbach resonance, and you see a signature of that in optical absorption. Is that
exactly
right?
Exactly?
Yeah,
so,
which is a bit unusual, because we usually when we think about a Feshbach resonance, it is a feature in the scattering amplitude of a hole or an electron, and so we'd probably be looking for transport signatures of that rather than optical absorption signatures. So are they linked in any way? So are there any transport signatures of the same Feshbach resonance?
Yeah, so in principle, I would say yes, but I want to remind, and maybe I didn't emphasize this enough, that you know, excitons in our experiments, in intra-layer exciton, like the one I've used here, is extremely short-lived. You know, this tight, I mean, the price that we pay for this rigid impurity is that the electron and hole overlap so strongly that they decay in a picosecond time scale.
Picoseconds, okay.
Yeah, so that's the main reason why there is this sizable line broadening in the system. So even though our temperature is very low, our basically radiative decay rate is not low, and it is actually not so far off from the Fermi energy. So maybe that's
right. Okay.
That was in a way that why I introduced this last example. And I should also say that together with Richard and Mikhail, we're looking into other possibilities. I mean, a bilayer system already exhibits several different possibilities for Feshbach resonances, and many of these have to do with coupling interlayer excitons into or scattering state consisting of interlayer excitons and charges, which also exhibit bound states and or can be tuned into bound states in a closed channel. And in that case, the interlayer excitons can be extremely long-lived, and therefore, in those examples, one could imagine studying transport features.
Right.
But with excitons with short lifetime, I think this is probably not very realistic. Leaving aside the issue that getting nice transport signatures at low densities is extremely difficult in the system.
Yes,
and that's also true for let's say expert transport groups, which we are not, and that has to do with the very strong Schottky features at the contacts.
Yes, thank you.
Any other question?
I'll ask a very quick question. Hey, Atac. So I think maybe I missed it. Were the electrons in this Feshbach resonance, were they delocalized or they localized, or I guess does it doesn't
question.
Yeah, okay.
So we have strong evidence that they are localized, even though we have a moire system, and I'll tell you the evidence. So basically, up to nu equals 1, we basically do not see any evidence for these sort of dispersive line shapes. So that tells us that for low densities, the holes that we inject into the system occupy sites, and we know that these are XM sites, for which there is no tunnel coupling. And we actually do see signatures of MOTS state formation in the 2 layers via the umklapp resonances. So basically, the way we arrived at that umklapp resonance as a tool for seeing Wigner crystal was actually through the MOTS states in bilayer systems. So that's kind of historically reversed. But basically, what we see is that nu equals 1 forms a very nice MOT state. But as soon as we go beyond single occupancy, possibly due to screening of the weak moire potential, we find that the holes that we inject into the system actually do not. We do not see any umklapp resonance, and we can tune the density and the splitting here continuously as we change the density. Whereas if the holes were localized in let's say certain sites, the MM sites, where the metal atoms sit on top of each other, which is the only site symmetrically allowed to exhibit hole tunneling, then we would basically have seen that there is no splitting up to nu equals 2, or all the splitting we will see will take place up to nu equals 2, and then there is no change. So the continuous change tells us that the excess, at least the excess holes that we have in the system, are delocalized and not pinned to specific lattice sites in the system. So yeah, okay. So that's what I could say about that.
Okay, thanks.
Okay, any other question? Okay, if not, then I stop recording.
Mm-hmm.